In chapter 3.4, when we talked about combining like terms, what we said is that as long as the variable is the same, then we can combine those by adding or subtracting the antecedent to the variable. Let me give you an example. If we had 3x plus 4x minus 2x, all right, now those x terms are exactly alike, which means now all we have to do is add or subtract the numbers that are ahead of that variable x. In this case, 3 plus 4 happens to be 7 minus 2. That would give us our answer of 5x. All right? So that's how we did that in chapter 3.4. Now what we're going to do is the same thing in chapter 9.3. So if you turn in your books to page 660, let's go ahead and demonstrate how this works. In problem number 2, we have 5 times the square root of 6 plus 3 times the square root of 6. And you already saw the answer, I just erased it. But since the radical is exactly the same, all we do is add the 5 and the 3 and get 8 times the square root of 6. However, if we drop down to number 16, now what we have under each of the radicals is different. So what we want to do is we want to simplify each of the radicals. And what we're going to look at is what numbers that are perfect squares can we divide evenly into each of those 3? Well, for the 108, it so happens that's the same thing as the square root of 36 times the square root of 3. And then for the negative 27, what we find is that's the same thing as saying the square root of 9 times the square root of 3. And then for the plus 75, what we realize is that's the square root of 25 times the square root of 3. Now, what we have is perfect squares, 36, 9, and 25. So what we get is 6 times the square root of 3 minus 3 times the square root of 3 plus 5 times the square root of 3. Now we have the same radical, the square root of 3 in all 3 of ours. So what we're going to do is we just take 6 minus 3, which is 3. 3 plus 5 equals 8 times the square root of 3. So what we've done is we've simplified those radicals to the point where now we have the same thing underneath the radical in all 3 cases, and we can go ahead and add those together. But now let's take a look at number 22, which is a little more complex. In number 22, we have the square root of 125y cubed minus the square root of 20y cubed. All right, what perfect square goes into 125? Well, it's 25. So if I pull out the square root of 25y squared, what do I have left? Square root of 5y. And then if I have the square root of 20, perfect square going into that is 4. So I'll pull out the square root of 4y squared times the square root, and what's left? 5y. Now, what this equals then is 5y square root of 5y minus 2y square root of 5y. Those combine now, 5y minus 2y gives me 3y times the square root of 5y. So there we have it. So that's how you do those. What you want, of course, is to find something that is the perfect, or the same underneath the radical, the same radical. In this particular case, it happened to be the square root of 5y. And then you can combine the like terms in front. Now, the only thing I'll caution you on is if we had done that and I had 5y times the square root of 5y minus 2 times the square root of 5y, I would be done because I couldn't combine the 5y and the 2. But since it was 2y, then I was able to combine those. Now let's take a look at number 36. starting with problem number 33, what we're supposed to do is multiply the radicals. In this particular case, this is just a sample. All you're doing is multiplying what's underneath there. So 5 times 7 is 35, and that times 3 is 105. So we have the square root of 105. The question is, do we have a perfect square that'll divide evenly to 105? Unfortunately, 4 won't, 9 won't, 25 won't, so we're done. But let's take a look at 40. If we multiply those across, what I get is the square root of 100. And that happens to be a perfect square, so the square root of that is 10. Now as we move down the page, let's take a look at problem number 42. These are cube roots, all right? And so you need to refer back to page 634 for your perfect cubes. But if we multiply 25x squared by 10x squared, we get the cube root of 250x to the fourth. Just so happens that one of the perfect cubes happens to be cube root 125. That's because 5 times 5 is 25, times 5 is 125, x cubed. And what we have left then is 2x. This then becomes 5x times the cube root, make sure I put my little cube up there, cube root of 2x. In number 48, what we're looking is that distributive property that we talked about, where we're going to multiply the square root of 2 times each of those expressions inside of the parentheses. When I multiply the square root of 2 times the square root of 10, what I get is 2 times the square root of 20. And then when I multiply through the square root of 2 times the square root of 40, I get the square root of 80. This then is equal to 2 times the square root of 4 times the square root of 5 plus the square root of 16 times the square root of 5. Well, now the square root of 4 is just 2. So what I end up with is 2 times 2 square root of 5 plus 4 times the square root of 5. Or 4 times the square root of 5 plus 4 times the square root of 5, and that's equal to 8 square root of 5. All right? The last one we have, number 52. Here we're again doing the distributive property, and I'm going to do that down below this because it's spaced. So if I take the cube root of 6 times the cube root of 32, what I end up with is the cube root of 196 minus the cube root of 24. Now, looking at our cube roots, what I realize is the cube root of 64 is a perfect cube, and what I have left is the cube root of 3 minus, and the cube root of 8 is a perfect cube, times the cube root of 3. Now what I get, cube root of 64 is 4, cube root of 3, minus cube root of 8 happens to be 2, and the cube root of 3 is equal to 2 times the cube root of 3. So there you have it. You can simplify all of these expressions through addition, multiplication, and those kinds of things. Best of luck.